Welcome to the deep dive. Today, we're starting with what feels like the simplest question in chemistry, maybe. What is an atom?
Seems simple, right?
Yeah, but our picture of it has changed so dramatically. We used to think, little planets spinning around a sun, electrons orbiting.
That old model. Cute, but not quite right. Science pushed further, and things got much weirder. And honestly, much more beautiful.
Definitely weirder. So, our deep dive today is into quantum theory and the electronic structure of atoms.
And this isn't just about tiny stuff. It's really about a whole new way of seeing the universe at its smallest level. It changed everything.
So, our mission for you today is to really unpack these core ideas, the ones that define modern chemistry. We'll look at how energy behaves in these, well, unexpected ways.
Ways classical physics just couldn't handle.
Right. And how light and matter do this weird dual thing, and where electrons actually are in an atom, or maybe where they aren't.
We'll try to make these complex ideas clear, give you some solid takeaways.
Okay, let's jump in. Where do we start? Energy.
Makes sense. Gotta start with energy. Basically, it's the capacity to do work or transfer heat.
And we usually talk about two main kinds.
Yeah. The big two are kinetic energy and potential energy. Kinetic is the energy of motion.
Like that helium atom you mentioned earlier, just zipping about.
Exactly. That movement is kinetic energy. Potential energy is different. It's stored energy. Energy of position or arrangement.
So, like the energy held in chemical bonds.
Perfect example. Or the electrostatic energy between, say, a proton and an electron. It's energy that's there because of how things are set up.
Got it. And there's that fundamental rule, right? The conservation law.
Absolutely crucial. The law of conservation of energy just states energy isn't created or destroyed in the universe. It just changes form.
It morphs,
It's
transforms.
always conserved. And we measure it in joules, symbol J. It's a pretty small unit, fundamentally.
Okay, energy basics covered. Now, light. This is where things started to get tricky for the old physics, wasn't it?
Oh, definitely. Light was a major puzzle. What we see, visible light, is just a tiny slice of this huge thing called the electromagnetic spectrum.
Radio waves, microwaves, infrared, UV, X-rays, gamma rays. It's all the same fundamental stuff. Electromagnetic radiation.
All of it. And it all travels as waves.
And waves have properties like wavelength, the distance between peaks.
Yep. Wavelength, lambda,
And,
and frequency, nu, which is how many waves pass a point per second, measured in hertz.
and amplitude. That's like the height of the wave, related to brightness for light.
Right. And the key relationship is that the speed of light, c, which is constant in a vacuum, equals wavelength times frequency. C equals c.
Now, how did we know for sure light was a wave? The
Yeah.
classic experiment.
The double slit experiment. Thomas Young, early 1800s. You shine light through two very narrow, close slits.
And you don't just get two lines of light on the screen behind it.
No, you get this complex pattern. Bright lines, dark lines, bright lines. It's an interference pattern. That only happens if light is behaving like a wave, where wave crests meet crests to get brighter, and crests meet troughs to cancel out. Undeniable proof.
Case closed. Light is a wave. Except.
When physicists tried to apply this beautiful wave theory to explain energy at the atomic scale, it just fell apart. Classical physics worked great for planets, for baseballs.
But for atoms, no good.
Utterly failed. It was a crisis.
Yeah.
Something fundamental was missing.
Enter Max Planck, around 1900.
Exactly. He was studying black-body radiation, the light given off by hot objects, and he made this leap. He proposed that energy isn't continuous. It's not emitted or absorbed smoothly.
But in chunks, discrete packets.
Precisely. He called these packets quanta, plural of quantum.
So back to my stair analogy, you can be on step 1 or step 2, but not step 1.5.
That's a great way to think about it. Or like a piano, only certain notes are possible. Planck even quantified it. The energy of one quantum, E, is proportional to its frequency, E site.
Where h is Planck's constant. Tiny number, 6.63 times 10 to the minus 34 joule seconds. But hugely important.
Monumentally important. Then, 5 years later, Einstein takes Planck's idea and runs with it. He looks at the photoelectric effect.
Right. Where light hits metal and knocks electrons off.
Yes, but the weird part was, it only worked if the light had a high enough frequency, a certain minimum threshold frequency. Below that, nothing happened. Didn't matter how bright the light was.
Brighter, low-frequency light just didn't do anything.
Nope. But if you were above the threshold frequency, electrons popped off. And even weirder, higher frequency light made the electrons come off faster, with more kinetic energy.
So Einstein's explanation was,
He said, okay, what if light isn't just a wave? What if it also acts like a stream of particles? He called these particles photons.
and each photon carries a quantum of energy, E equal.
Exactly. So hitting the metal with light is like bombarding it with these tiny energy bullets. If a single photon doesn't have enough frequency, it can't knock an electron out, period. It's a one photon, one electron interaction.
It needs that minimum punch, and
Right.
higher frequency means a harder punch, so the electron flies off faster.
Precisely. And it's amazing how this stuff shows up everywhere now. Garage door sensors use it, motion detectors, solar cells.
Even night vision goggles.
Yep. They take faint infrared photons, use the photoelectric effect to turn them into electrons, amplify those, and create the image you see. It's quantum mechanics in action.
So this leaves us in a strange place. Double slit says wave, photoelectric effect says particle, light is both.
That's the wave-particle duality, a core concept in quantum mechanics. It was baffling, but it opened the door to understanding the atom itself.
Which brings us to Niels Bohr and the hydrogen atom. What was he trying to solve?
He was looking at atomic line spectra. When you heat up a gas of an element or run electricity through it.
Like in a neon sign.
Exactly. It doesn't glow with a continuous rainbow. It emits light only in very specific colors, specific wavelengths. Each element has its own unique pattern, like a barcode.
A spectral fingerprint? How we know what stars are made of, right?
That's how. So Bohr said, okay, maybe electrons inside atoms can't just be anywhere. Maybe they can only exist in specific energy levels or orbits, quantized levels.
Like the stairs again, not the ramp.
Just like the stairs. He numbered these levels, N1, N2, N3, and so on. N1 is the lowest energy state, the ground state.
And anything higher, N2, 3, 4. Those are excited states.
Correct. An electron can jump to a higher level if it absorbs the exact right amount of energy, and when it falls back down from an excited state to a lower one.
It emits a photon with energy equal to the difference between the levels.
Precisely. And that's why you only see specific colors, specific frequencies in the line spectra. They correspond to these allowed energy jumps. Like electrons falling to N10 and hydrogen give you the visible Balmer series lines.
And Bohr even had an equation for the energy of these levels.
He did, for hydrogen at least.
Yeah.
N equals 2.18 times 1018 joules times 1n and 30. The energy depends only on that principal quantum number, n. Fixed levels.
Okay, so Bohr gives us quantized energy levels, fixed orbits, sort of. But then things got wavy.
Things got very wavy. Thanks to Louis de Broglie in 1924. He had this incredibly bold thought. If waves like light can act like particles.
Then maybe particles like electrons can act like waves.
Exactly. It seems crazy, but he proposed it. He suggested an electron in an atom behaves like a standing wave.
Like a guitar string. It can only vibrate at certain frequencies, creating those nice standing wave patterns with nodes.
Perfect analogy. De Broglie said an electron wave had to fit perfectly within its orbital space. If it didn't, it would interfere with itself and cancel out. Only certain wavelengths and therefore certain energies were allowed.
And he had an equation for this wave.
Yep, the de Broglie wavelength.
Yep.
OOP, where h is Planck's constant, m is the particle's mass, and u is its velocity.
Was there proof? Did anyone see electrons acting like waves?
There was. Experiments involving electron diffraction. They shot beams of electrons, which are definitely particles, at crystals.
Instead of just scattering like tiny balls, they
Produced interference patterns, just like X-rays, which are waves, do when they diffract through a crystal. It was stunning confirmation. Matter has wave properties.
mind-bending. But does my baseball have a wavelength?
Technically, yes. But calculate it using de Broglie's equation, and because the mass m is so large, the wavelength was astronomically small, something like 10 to the minus 34 meters. Way too small to ever detect.
So this wave stuff only really matters for tiny things, subatomic particles?
Exactly. For electrons, protons, neutrons. Their wave nature is significant. For everyday objects, it's completely negligible.
Okay, electrons are waves and particles in quantized energy levels. But Bohr's idea of neat, predictable orbits, that didn't last either, did it?
It couldn't. Werner Heisenberg delivered the next conceptual blow with his uncertainty principle in 1927.
The one that says you can't know everything precisely at the same time?
Right. Specifically, you cannot simultaneously know both the exact position and the exact momentum, which is mass times velocity, of a particle like an electron.
The more you pin down one, the fuzzier the other gets.
Precisely. There's a fundamental limit to the combined precision. If you try to know an electron's position really, really well,
Its momentum, its velocity would become incredibly uncertain. So uncertain that the idea of it following a defined path and orbit just dissolves.
it completely undermines the idea of a fixed orbit. The uncertainty in an electron position, if you tried to know its velocity reasonably well, could be bigger than the atom itself.
Wow. So Bohr's model was a crucial step, but ultimately limited.
Yes. It worked beautifully for hydrogen, but couldn't handle atoms with more electrons, and it didn't account for this inherent uncertainty or the wave nature properly.
So where did physics go next? Who put the wave and particle ideas together with uncertainty?
That was Erwin Schrödinger, around 1926. He developed a sophisticated mathematical framework, the famous Schrödinger equation.
Which is central to modern quantum mechanics. What does it describe?
It describes the behavior of electrons in atoms, incorporating both their wave-like and particle-like properties. Its solutions are called wave functions, represented by the Greek letter psi.
Does the wave function itself tell us where the electron is?
Not directly. Psi itself is a bit abstract mathematically, but its square, pim, has a very important physical meaning. It gives you the electron density.
Meaning, the probability.
Exactly. Represents the probability of finding the electron within a specific, tiny volume of space around the nucleus.
So we ditch the idea of orbits, these fixed paths.
Completely gone, we replace them with atomic orbitals.
Which are what, exactly? Probability maps.
That's a great way to put it. An atomic orbital is a region in 3D space around the nucleus where there's a high probability, typically, say, a 90% chance of finding the electron. It doesn't tell you how the electron moves, just where it's likely to be.
So orbitals are fuzzy clouds of probability, not little racetracks.
Precisely. And to describe these orbitals, their size, shape, orientation, and the electrons within them, we need a set of identifiers.
The quantum numbers, like an electron's address.
Exactly. 4 numbers are needed to uniquely specify the state of an electron in an atom.
Okay, let's break them down. First one.
The principal quantum number, n. This is the main one Bohr used. It basically tells you the energy level and the overall size of the orbital. N can be 1, 2, 3, any positive integer. Larger n means a larger orbital, further from the nucleus, and generally higher energy. We sometimes call these shells.
Okay, size and energy level. What's next? L.
Right, the angular momentum quantum number, L. This one determines the shape of the orbital. Its value depends on n. L can be any integer from 0 up to n1.
And we use letters for these shapes.
I do. If L is 0, it's an s orbital, which is spherical. If L1, it's a p orbital, which has a dumbbell shape. L2 gives a d orbital, usually with 4 lobes, like a cloverleaf, or sometimes a dumbbell with a ring. L3 is an f orbital, with even more complex shapes.
So within a shell, defined by n, you can have different shaped subshells defined by L.
Exactly. Shell N1 only has a L0 and s orbital. Shell N2 has Le0 and s orbital, and L1 p orbitals. Shell N3 has sp and d orbitals, L0, 1, 2, and so on.
Okay, size and shape L. What else?
Right.
Orientation.
That's the magnetic quantum number, ML. This tells you how the orbital is oriented in space relative to other orbitals. Its possible values depend on L, ranging integers from ml through 0 to plus L.
So for n s orbital L0, ml can only be 0. Makes sense. A sphere only has one orientation.
Right, but for p orbitals, L1, ml can be -1, 0, or +1. That corresponds to the 3 p orbitals, p, x, pi, pz, oriented along the x, y, and z axis. They have the same shape and energy, just different directions.
And for d orbitals, L2, ml can be -2, -1, 0, +1, +2. So there are 5 d orbitals with different spatial orientations.
Correct. These 3 numbers, nl and ml, together define a specific atomic orbital.
But you said 4 numbers for an electron. What's the last one?
The last one describes a property of the electron itself, not just the orbital. It's the electron spin quantum number, EMS.
Spin. Like the electron is actually spinning.
It's a helpful analogy, but it's really an intrinsic quantum mechanical property, like charge or mass. Electrons behave as if they have a magnetic moment, which we call spin. It can have one of 2 values, +12, spin up, or -12, spin down.
So every electron acts like a tiny magnet.
Essentially, yes.
Oh.
This spin is crucial for understanding how electrons fill orbitals.
Okay, so we have the address system. NL describe the orbital, the street, house number, room. And EMS describes the electron in that room, spin up or spin down. How do we use this to build atoms? Fill in the electrons.
Now we need the rules for electron configuration, how electrons are distributed among the available orbitals.
Rule number 1, the big one.
The Pauli exclusion principle. Wolfgang Pauli figured this out. It states, no 2 electrons in the same atom can have the exact same set of all 4 quantum numbers, N, L, ML, MS.
Meaning, if 2 electrons are in the same orbital, same N, L, ML, they must have opposite spins, 1 + 12, 1 national 12.
Absolutely. That's the direct consequence. An orbital can hold a maximum of 2 electrons, and only if they have opposite spins. This principle is fundamental to the structure of matter.
Okay, Pauli exclusion. What's next? How do we know which orbitals fill first?
That's the Aufbau principle. Aufbau is German for building up. It just says that electrons fill the lowest energy orbitals available first, before occupying higher energy ones.
Makes sense. Fill from the ground up, like filling seats in a theater from front to back.
Pretty much. You fill ones, then twos, then 2p, then threes, then 3p. Though the order gets a bit more complex later on, like fours fills before third, because of how the energy levels actually overlap.
Right, there's a specific filling order based on energy. Now, what if you have orbitals with the same energy, like those three p orbitals, px, p, pi, pz, in the p subshell? They're called degenerate, right?
Exactly. Degenerate orbitals have the same energy. And that's where Hund's rule applies.
Hund's rule. The seat rule.
Huh. Yeah, that's the common analogy. It says that for degenerate orbitals, electrons will fill each orbital singly with parallel spins, all spin up, for example, before any orbital gets a second electron, which would then have the opposite spin.
So if you have 3 electrons going into the 3p orbitals, they go 1 in px, spin up, 1 in px, spin up, 1 in px, spin up. They don't pair up immediately.
Correct. They start out first with the same spin. There's a slight energy advantage to this arrangement, maximizing parallel spins.
And this whole electron configuration thing, especially unpaired electrons, it connects to magnetism, doesn't it?
Directly. If an atom or ion has one or more unpaired electrons sitting alone in orbitals according to Hund's rule, it will be paramagnetic.
Meaning it's attracted to an external magnetic field, like oxygen. O2 is paramagnetic.
Good example. Oxygen has 2 unpaired electrons in its molecular orbitals. But if an atom has all its electrons paired up, 2 in each occupied orbital with opposite spins, it's diamagnetic.
And diamagnetic means it's weakly repelled by a magnetic field, like neon or nitrogen N2.
Exactly. All electrons paired, spins cancel out, weakly repelled. Unpaired electrons net spin, attracted.
It's amazing how this all ties together, and the periodic table itself is basically organized by these electron configurations, right?
Absolutely. It's a direct map. We often use shorthand, the noble gas core notation. Instead of writing out all the electrons for, say, potassium, 19 electrons, which would be 1s2 s2 minori 3p4 Sitchis.
Which is long.
You just find the previous noble gas, argon, 18 electrons, and write its symbol in brackets, then add the remaining electrons. So potassium is just R4, Cydia, much cleaner.
And the blocks of the table are S block, B block.
They correspond directly to the subshell being filled. The S block, groups 1 and 2, are filling this orbital. The P block, groups 13, 18, are filling orbitals. The D block in the middle are the transition metals, filling orbitals.
And those lanthanides and actinides usually put at the bottom, that's the F block, filling orbitals.
Precisely. The table's structure is the Aufbau principle laid out visually.
Though there are a few quirks, right? Exceptions to the filling order.
Ah, yes, the famous ones, like chromium Cr and copper Q. You'd expect chromium to be R4C3DOs based on the simple Aufbau order.
But it's not. It's R4C3EO. It bumps an electron from 4s up to 3.
Right. And copper, you'd expect R4C3DO, but it's actually R4C3Drs.
Why do they do that? What's the advantage?
It comes down to stability. There's a special stability associated with having a subshell that is exactly half filled, like Da for chromium, or completely filled, like D for copper. That slight extra stability is enough to make this configuration lower in energy than the expected one.
So nature prefers these symmetrical half-filled or fully filled arrangements when possible.
It seems so. It's a subtle but important refinement to the building up process.
Wow. Okay, we've covered a lot of ground. From basic energy through the wave-particle weirdness, Bohr's levels, uncertainty, Schrodinger's probability clouds, and finally the quantum number addresses and filling rules.
It's quite a journey from the simple planetary model. We've moved into this probabilistic, quantized world where particles are waves and electrons have these specific addresses dictated by N, L, M, L, and Ms.
So what's the big takeaway for someone listening? The so what?
The so what is huge. This quantum picture isn't just some abstract theoretical exercise. It is the absolute foundation for understanding everything else in chemistry. Why atoms bond the way they do, why molecules have specific shapes, why different elements have their unique chemical properties.
It explains the why behind the periodic table, behind chemical reactions, behind the materials that make up our world.
Exactly. It's the fundamental rule book for how matter behaves at the atomic level. Understanding this unlocks the why for so much the chemistry you see and do.
It really changes how you view even simple things.
It does. And maybe a final thought to leave you with. Think about Heisenberg's uncertainty principle again.
That fundamental limit on knowing both position and momentum?
Right. If we literally cannot know everything about even a single electron, with perfect precision simultaneously. What does that really imply about the nature of reality itself? About what it means to know something, especially at this most fundamental level?
Yeah, that's something to chew on, a limit built into the universe itself.